This is for homework problem number 3, and we're looking at relations versus functions. So what is a relation? So a relation is just a little rule that assigns one thing, for lack of a better word. So I'm not going to put value or number because it really could be anything. It could be a shape, it could be a word, it could be anything. So a relation is a rule that assigns one thing to another. There's no restrictions on it, no rules, no guidelines it has to follow. I could literally assign anything to anything else and it would make a relation. So I'm going to do let square go with 7. I guess that's kind of a rectangle. I don't know. I'm going to say the word turkey goes with the letter R. And I'm going to let square again go with the color red. And my little snowman. Snowman can go with the star. Alright, now as crazy and random as this seems, this is a relation. I am just assigning different values to other different values, right? Mapping things together, if you will. And there's no rhyme or reason to it. I don't have any restrictions, as we said. So this is a relation. What makes a function and not just a relation, because every relation is a function, but not every function is a relation, because a function puts a restriction on it and says, all right, hang on, guys, stuff's getting crazy. We got to have some rules, some rhyme or reason to stuff. So a function puts a limitation on it. It restricts the x value, so that every x value, so it restricts x's to only one y value. And so you can see that this causes a problem for my relation now, because these are coordinates, and so the first value is representing my x, my domain, my input, and the other randomness, the second thing in the parentheses, is representing my y value, so my output. And the function puts a restriction on it. It says, okay, you can still be crazy, but your x's, for every x, you can only assign it to one y value. All right, no more being promiscuous all around the block. You pick one, and that's it. All right, so this would still be a relation, but it can no longer be a function. Because why? Why would this not be a function anymore? I have different values assigned to my squares, or my rectangles, whatever I called them, right? My square is going to both 7 and to the color red, or the word red. So this is a relation, but not a function. Alright, so this is just one representation, though, of how I could see a relation or a function. I could have a set of coordinates, set of ordered pairs that are listed out. Same thing with a table. I could have a table of values. And there's a couple of other different ways that we generally see relations or functions represented. So again, with the ordered pairs, so if they're listed out, it's pretty easy to see. I can look at all the x values and just make sure they only have one single y value. So let's look at an example, a couple examples real quick. So I can list my ordered pairs as a table. Alright, so I have this set of ordered pairs in the form of a table. And I want to know, is it a relation or is it a function? It's a relation. Actually, that's bad wording. Because again, every relation, or every function, is a relation. But that's okay. It's a relation. Why is it not a function? Why is it not a function, Julia? Exactly. The negative 2's for my x values get mapped or paired with two different y values, 1 and 5. Negative 3 is on there twice, though. Why does that not create an issue? Because it's mapped to the same y value, right? So I'm just repeating the same x value. And so I can actually take that out without any issue because I already have that ordered pair in there. But the 2's, or the negative 2's, create an issue because they are both mapped to different y values. And since they are different, this is forced to be a relation and not a function. Okay. Alright, so how else could I see this represented? Well, how else did we see functions? I could get a list of ordered pairs. I could also see a graph. And so if my relation is given to me in the form of a graph, so I don't have listed ordered pairs anymore, I just have a graph. And I want to tell, is it a relation or is it actually a function? It looks a little different than the graphs that you might have seen in Algebra 1 or Algebra 2, but the same thought process carries over. My x values can only have one y value for it to be a function. Now, I'm going to pick, let's say this point right here. Here's an x value. How many y values go to this x value? I have two, right? The one directly above it and the one directly below it. So a single x value maps to two different y values. Is this a function? No, it's not a function, right? What we just used is called the vertical line test. Now, the vertical line test says that if we can draw, if a vertical line can be drawn anywhere at any point, and it passes through more than one point, then the relation is not a function. And all those words are exactly what we just did. If I drew a vertical line at this x value, then it does pass through more than one point. It passes through 2 points. And there are actually several places that I could do this on this graph, but all I need is one. If it happens at one place, then automatically it is no longer a function. It is just a little bitty baby relation. All right? So if I can draw a vertical line anywhere and have it pass through more than one point, then the relation is not a function. So this is not a function. So an example, so this is an example of not having an example of one that actually is a function. We're going to go back to the basics here. What type of function is this? It's linear, right? It's just a line. And it is a function, so spoiler, it's a function. But notice, if I draw a vertical line anywhere on this graph, I am only going to pass through my linear function one time, right? Here's one, 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 one. So it is indeed a function. FNCT is the abbreviation for function. It is a function. Now the third representation that we could have, so we've looked at ordered pairs and tables, we've looked at graphs. So the third representation we have of a relation or function is the actual equation of the rule. And again, the same thing carries over. My x's, if I plug in an x value, I should only get back a single y value. All right, so is y a function of x? Is y a function of x? If y is a function of x, then if I plug in an x value, I should only get one single y value back out, right? There should only be one possible y value. All right. So when I'm looking at my equation and trying to determine if x is a function, or if y is a function of x, I need to get y all by itself. If I already have y all by itself, then awesome. Then I'm looking at, since y is already by itself, when I plug in an x value, how many numbers am I going to get back? Just one, right? This one kind of makes it very simple. No matter what number I plug in, when I square it, how many numbers do I get back after I square it? Just one, right? 7 squared gives me 49. Not negative 49, not some other random number. I simply get one number back. And if I add 4 to it, again, I only get one number back, right? So it kind of seems silly and simple. If my y value is all by itself, then it should generally be fairly simple to figure out how many values am I getting back. If I plug in x, I only get one value for y, so this is a function. All right, so let's look if y is not by itself. I got to get y by itself. So let's say I have y squared plus 7 equals x. All right, and the same question, is y a function of x? Well, in order to determine that, really I need to get y all by itself first. So I'm going to solve this for y. I want y all by itself. So I'm going to subtract 7 from both sides. I get y squared equals x minus 7. And again, I want y all by itself. How am I going to get that? What do I need to do? I need to take the square root. And when I take the square root, what do I have to account for? Positive or negative, right? Because it's squared, which means it could have either originally been positive or it could have originally been negative. So when I take the square root, I have to account for positive or negative square root of x minus 7. Now this tells me if I plug in a single value for x, then either y will equal a positive square root of x minus 7, and y will equal negative square root of x minus 7. So I plug in a single value for x, and I end up getting two different values for y. Function or no? No, this is not a function at all. All right? If I plug in a single value for x, I get two separate, a positive and a negative value for y. So this is not a function. Now, when you're solving these, trying to figure out if y is a function of x or not, this issue came because I had an even exponent on y. Anytime you have an even exponent on y, So even being 2, 4, 6, 8, 10, 12, so on and so forth, you will have to account for the positive and for the negative. So this happens every time the exponent is even. Now the odd exponents, I don't have to account for the positive or negative because I can take an odd root of a negative number, right? So there's no longer any guessing, right? A negative number cubed still gives me a negative number back out, so it's not deceptive, right? So this plus or minus only comes into play when I'm solving and I have an even power, even exponent, okay? Any questions?